Yes, sir.
Yeah. So in the previous class, we have derived expression for the intensity of a diffraction pattern produced by single slit. This is the single slit equation. We have derived the expression, which is one of the important questions for you also. And by using the vector addition, we found that the resultant amplitude at any angle of theta diffraction is am sine alpha by alpha, and the intensity at a given diffraction angle is im into sine alpha by alpha whole square, because intensity is amplitude square. Thereby, we are now calculating conditions for central maxima or 0th order, or we say principal maximum. So we have done like this. And then we have seen the positions of minima also. The diffraction pattern consists of alternate maxima, minima, and the maximas are of not equal intensity. They decrease with increasing order or increasing n value. So this next maximas, we call them as secondary maximas. So we call this as the, okay, what we have called this as principal maxima. These are the minimas. These are the secondary maximas. And we have derived a condition for central maxima, that is theta is equal to 0, which is undeviated beam. And minima positions, we have seen it by supposing that sine alpha equal to 0, but not alpha equal to 0. Therefore, this alpha value will take the values equal to plus or minus n pi, where n take all integer values 1, 2, 3. And thereby we have got a condition for minima as E sin theta equal to n lambda. This is one of the important conditions for solving problems for single slit. Okay, and then we will now start for the condition for secondary maxima. Okay, so I now start the condition for secondary maximum. So we have derived that I equal to Im sine alpha by alpha whole square is the intensity pattern for, okay, this is intensity distribution function, IDF we call it as. Now to find the secondary maxima, we have to do the di by df and df by d alpha, that is to find maxima minima from your mathematics, I equate it to 0. So can anyone find out the value of this? So this I can take out. I can write by d alpha of sine square alpha by alpha square, or I write like this. So can anyone tell what is this value? The differentiation of sine alpha by alpha whole square. How to do this? The x by y form. This is nothing but am square, you can write. Okay, because it's intensity. So I'll write here 0 equal to Im. So what is the differential of sine alpha by alpha whole square? Anyone? Can you tell me? Can you do and tell me? Roll number 59. Can you do it? Huh? So this will be, I'll write this equation, the solution of this differential of this equation as simply it is alpha square, alpha for 4, I'll get alpha square sine 2 sine, I'll write 2 sine alpha for sine alpha, okay, I'll get cos alpha, followed. So what is the next step? Can anyone tell me? Okay, here I am just switching off my video. And roll number 59, can you tell me the next step? What should be the next term in this? I'll get minus 2 alpha sine square alpha. So if I cancel throughout here one alpha square, alpha I can cancel here. Otherwise, I'll write this as is equal to Im into alpha I can take 2 also I can take out, and sine alpha also I'll take out. If I take 2 alpha here, I left with okay uh, alpha cos alpha, okay, minus 2 alpha sine square has gone. I have only here sine alpha, and divided by we have alpha 4. And from this I can say that this alpha and this alpha 4 can be cancelled. I'll get alpha cube, and therefore I will write this as Im into 2 sine alpha by alpha. I'm writing this. I've taken 1 alpha from this, and left outs are alpha cos alpha minus sine alpha, okay, alpha cos alpha minus sine alpha by alpha square. Because I have to have an alpha cube here, I have taken 1 alpha here, 1 alpha square. I'll get it equated to 0. Yes, therefore, since Im is not equal to 0, okay, I'll write Im that is not equal to 0. I will write 2 sine alpha by alpha into, okay, alpha cos alpha minus sine alpha by alpha square is equal to 0. Did you follow this, all of you?
Yes, sir.
Yeah. Now you know sine alpha by alpha already, okay, which is of course amplitude here. And if I want to get secondary maxima, okay, I have to see that what are the values that alpha should take it. To do this, what I find it out is that, okay, I will write here this product of two. This is the product of two terms. Okay, so we have first term here. This is the first term. Okay, and this is the second term. So if product of two terms 0 means this term must be 0 and this term also must be equal to 0. But here sine alpha is equal to 0 is a one requirement, since alpha should not be 0 here. And here the second requirement is cos alpha minus sine alpha is equal to 0 here. Okay, that means this is 0 or this is equal to 0, then entire one product is equal to 0. Therefore, we have two options, sine alpha equal to 0. But sine alpha equal to 0, we have already taken this sine alpha is equal to 0 for minimum positions. Therefore, the option that left out is here. This is the condition for secondary maximas. Okay, so this is the secondary. This gives you secondary maximum. Secondary maximum. From this, I'll write alpha cos alpha minus sine alpha is equal to 0, which means alpha cos alpha is equal to sine alpha, which is equal to alpha is equal to sine alpha by cos alpha. I'll get, or I'll get alpha is equal to, can you tell me what is the value of alpha? 10 alpha, good, is equal to 10 alpha. Okay, now if I solve for alpha, for which values of alpha this equation is satisfied, I will get condition for secondary maxima. So to get the condition for secondary maxima, I have to solve this. Instead of solving this mathematically, I solve this equation by graphical value. Okay, to find value, I say to find value of alpha. Okay, we have to find the value of alpha that satisfies the secondary maxima. I will take, okay, solve graphically. Solve graphically. So I do graphical analysis to get values of possible alpha. Solve graphically for possible alpha values. Alpha values for secondary maxima. Secondary maxima. So what I'll get now, I have to say it. I'll write to solve graphically. I'll take y is equal to alpha is a straight line, but alpha is equal to tan alpha, therefore y is equal to tan alpha. I have now two equations. It is a straight line, okay, passing through origin, and this is a tan graph, tan theta graph. Therefore, if I superpose these two on the same graph where the straight line cuts tan alpha curve, those are the solutions for this curve. That means the intersection of y equal to alpha line on, okay, y equal to tan alpha curve gives the values of alpha for secondary maxima. Secondary maxima. Therefore, I draw here a graph to find out this one. To draw the graph, now I am taking, okay, somewhat this, and suppose say I draw here a straight line, something like this. Okay, then I draw another line here, maybe, okay, I'm taking another line somewhere here. I'm drawing. Okay, 1 minute. I draw. So I draw here another line somewhere. And I suppose say this is now 0. Now I will add the lines for different values of alpha. Okay, those values I'll take here. This may be pi by 2. I take one line here. I take 3 pi by 2. Here another one. And maybe 5 by 2. Here I'm taking. On either side, this also I take here pi by 2. And here also I take minus 3 pi by 2. And here I take maybe say minus 5 by 2. And so on you can take it. Now I want to extend these, okay, I'm taking the shapes and this one. I am now drawing with maybe a different color. Suppose I take here different color. So I am taking a green color and I'll draw the shapes. Okay, this is the line that is passing through pi by 2. Okay, then I draw another line passing through 3 pi by 2. Similarly, I draw one more line at 5 by 2. Okay, so these lines are at pi by 2, 3 pi by 2, and 5 by 2. Similarly, I draw lines at the negative side, that is, okay, I say this is at minus 5 by 2. I have to write. So all of you draw these curves so that you can easily find the solution for this. So I draw here one more line at here, and you can draw one more line here. So I'm drawing one more line here. Okay. Now I have to draw the curve y is equal to alpha. Y is equal to alpha is a straight line passing through origin. Therefore, I now draw a straight line passing through origin, something like this. This is a straight line passing through origin. Okay, and I will now extend this in this direction also, so that, okay, this is a straight line passing through origin, which is y is equal to alpha straight line. Now I have to draw tan alpha, and you know the tan alpha curve. So to draw the tan alpha curve, okay, I am now taking the tan alpha curve. You know that tan 0 is 0. Okay, tan 0 is 0. And can you tell me what is the value of tan 90 degrees, tan pi by 2? What is tan?
Undefined.
Undefined. Okay, so therefore the tan value starts from 0, goes like this, and becomes a maximum like this. Similarly, if I go for negative, this tan curve starts here somewhere, and okay, slowly comes, and it comes like this, and it becomes infinity at minus 1. Therefore, the curve of a tan, if you draw tan curves are starting from 0 and becomes, okay, sorry, I'll try it again. Okay, if I draw from here, I draw here slowly, okay, and I'll get here, and it becomes infinity here. So the tangent, that is the y equal to alpha line, and the tan alpha curve, this is tan alpha curve, this is tan alpha curve, okay, are now meeting at 0, that is 1 point. Next, if I go here somewhere, if you look at this curve, okay, again tan is equal to 0, but if I start drawing the curves at 3 by 2, tan becomes again infinity. Okay, so the curve starts here, goes and slowly, and becomes infinity here. Similarly, at minus sign also, it goes to infinity. Okay, so therefore the curves are, the tan curves will get it as. So the tan curve comes here and becomes infinity at this position. And similarly, if I draw another curve also here, okay, this 3 pi by 5 pi by 2, the tan curve becomes, okay, infinity. And here also, if I look at here, the curve comes, and at this position, it becomes infinite. These are nothing but tan alpha curves. Similarly, I have to draw from here also. If I want to draw here, the at infinity it becomes like this, okay, and comes here and becomes 0, and at this goes here, and this line goes right, okay, and comes here, and this cuts here. This is cutting here. This is cutting here. These are the intersection points. Similarly, also I can draw a 5 by 2, it is infinity, becomes 0, and then it goes on increasing and becomes like this. These are the tan alpha curves. Okay, so therefore you can see that the tan alpha curves and alpha curves are meeting at points very close to pi by, okay, this is pi by 2, nearly pi by 2, but not exactly equal to pi by 2. If you
Pi
see
by
here,
2.
yeah, but not exactly 5 by 2. They are now, okay, being added at some points like this. So therefore, okay, we say that they are not exactly touching at 3 pi by 2, 5 by 2, but mostly they are going somewhere here very near to it. Therefore, these intersection points are the solutions for alpha. Hence, we say that alpha takes for secondary maxima, alpha values occurs, okay, at 0, it is exactly coincided, It is there, but it is not exactly at 5 by 2, because see this curve, if I see this curve is not exactly 5 by 2. If I see it, it is not exactly 5 by 2. So this is also, okay, if I say it, it is not exactly at 3 pi by 2. This is also not exactly at 5 by 2. Therefore, it was observed that secondary maximas will appear at plus or minus, actually should be pi by 4, but okay, it is not exactly touching. It may be touching at plus or minus 4.3, plus or minus 2.46 pi. Okay, and it may be 3.47 pi instead of 3.5. Therefore, approximately you can take the positions of secondary maxima, positions of secondary maxima will come, okay, at alpha equal to 0. I roughly take it as pi by 2. Okay, 1 pi by 2 is okay, pi by 2, or sorry, 3 pi by 2, 1.5. I take then 5 by 2 likewise. That means secondary maximas will be coming at points, okay, equal to 0. I'll take it, I will take that. So therefore, I'll get it as 0, 3 pi by 2, then 5 pi by 2, then I'll get 7 pi by 2, and so on. Hence, we have to see that if I want to draw a curve for the entire diffraction, okay, I'm taking here, I will get here the maximum. Okay, suppose I'll draw here, the maxima will be central maxima, we call it as, that central maxima is for theta is equal to 0, we have seen it. Then we have secondary maxima here, again minima, and again secondary maxima, but the intensity decreases. And here we get maxima, here we'll get minima, here, and it was like this. On this, I have taken alpha. On this, I will take sine alpha by alpha whole square with IR. Therefore, we can say that this as central maxima or principal maxima, we call it as this principal maxima. Okay, this appears theta is equal to 0. And these are called minimas. If I take different color, these we call it as minima positions. These are minimas. Minima which appears at alpha is equal to 0 or alpha equal to n pi. We have seen it because the minimum condition is E sin theta is equal to n lambda. So we have seen it. So therefore, alpha will take n pi values with, okay, n equal to 1 to 3. Hence, we will get alpha equal to n pi. Okay, alpha equal to n pi plus or minus, where n will take 0, 1 to 3 values. And we have now another in between the minimas, if you say, okay. So we have one minima, another minima, another minima. Between another minima, we have another maximas. Okay, many maximums are there. These maximums, we call them as secondary maximas. Secondary, but their intensity is decreasing as order is increasing. Secondary maximum. So these secondary maxima occurs for which alpha will take the values of, okay, 0 is actually given to this, therefore 0 is not given to this. It will be at 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on. So therefore, a diffraction pattern consists of alternate dark and bright fringes of decreasing order. That is very important. Decreasing order. Therefore, we have now the equation that when I write, okay, we have alpha for secondary maxima. If you go it, this is the equation. Otherwise, I write alpha will take a value of 2n plus 1, okay, pi by 2 I can write, where n will take the values of 1, 2, 3, and so on. Okay. Therefore, it may be plus or minus, I can write alpha. If I put n equal to 1, I'll get 3 by 2. 0 is not there. Okay. If I put a 2, I'll get 5 by 4. Therefore, I'll write alpha equal to 2n plus 1, okay, into pi by 2. But you know that alpha n is nothing but pi sine theta, okay, by lambda. This is equal to, now I'll write plus or minus 2n pi, you can equal to plus or minus, because I have taken this side and also this side. Okay, plus or minus n into pi by 2. And you can cancel pi on either sides, then you'll get e sine theta is equal to 2n plus 1, okay, plus or minus, of course. Okay, I'll get plus or minus 2n plus 1 into, I'll get lambda goes the other side, therefore I'll get lambda by 2. Okay, so this is the condition for secondary maxima. Secondary maxima. And we have seen that for central maxima, okay, condition is theta is equal to 0. And for minimum, we have seen minima, the condition is E sine theta if you have derived it n lambda. Okay, so these are the three conditions for maxima, minima, and central maxima. So this is the condition for, okay, E sine theta is equal to n lambda. If you want to put plus or minus, you can put plus or minus lambda. Here also I can put plus or minus. So these are the conditions for maxima, minima, and central maxima. But if you see, the width of the central maxima is most important. This is called width of the central maximum, or width of these maximas. So width of central maxima. Okay, so the width depends on what factors? Or if from this also you can say it depends on E. If E is smaller and smaller, then the width is larger and larger. Therefore, the conclusion is that the width of, okay, central maximum, central maximum, if you take central maximum, I'll write is directly proportional to lambda. Okay, that means it depends on the wavelength of incident light. And the second one you have to remember is the width of the central maxima is, if I write the same, central maxima is inversely proportional to, okay, I'll write inversely proportional to E, where E we call it as slit width. Therefore, if the slit is narrow and narrow, then the central maximum become broader and broader. This is the pattern you have already observed when you have done the experiment called lasers. Here we have seen the bright spot, very bright spot like this, and here the spot has decreased intensity, decrease further, decrease further, decrease further. Likewise, you have seen the maximas and minimas. Okay, here, okay. So therefore, we can say that we will get the second maximas at positions. If I want to draw here, this is the maxima, secondary maxima is here, but like little intensity. It is further little intensity. It is further like this. Here also I have intensity here, goes like this. Therefore, we call them these as orders. As order is increasing, the intensity is decreasing. So more the order value, less will be the intensity. But zero order will have maximum intensity because the curve shows the maximum amplitude here. Okay, this is the conditions for maxima and minima for a diffraction pattern, which is the derivation what we have derived. Now in case, okay, I would like to see, this is the case if I want to have, okay, here only one slit we have taken. What happens if I take two slits? That is called double slit experiment. So double slit. So we'll now look at diffraction due to double slit. Diffraction due to double slit, which is not there in the syllabus. That's why I don't take too much of time to give derivation for this. But still, we want this derivation since we want to use it for n slits. Okay. Hence, I will tell you only the thing how we are getting the expression for double slit. So I am writing again the heading of this double slit. You can also put here. So we will now write diffraction due to a diffraction pattern, diffraction due to double slit. Double slit. You have already done this double slit in interference as Young's double slit experiment. Yes, can you remember that? Now, in double slit experiment, what I suppose here is that in double slit diffraction, I take here a source. A source gives you a light rays coming from it, maybe like this. The light ray may come like this, and the light ray may come like this. But we are now in Fraunhofer class of diffraction, therefore we need to use lens. Hence, I keep a lens, a convex lens here. Okay, this is the lens. This is the source, and source will have a wavelength lambda. And then I will say that the light is falling on the lens. The purpose of the lens is to make the light rays parallel. So that's why we say in Fraunhofer diffraction, the incident light is a plane wave front. In Fresnel's class, it is not plane wave front, it is a spherical wave front. Therefore, as I said, double slit, I now take the double slit here. The double slit will have two openings. I have one opening of it separated by separator like this. And this is the center of the slit. This is the center of the slit. And we call it as double slit. Two openings are there whose dimensions are comparable with the wavelength of the light. And suppose say the width of the slit, okay, I am taking the width of the slit as E as we have taken earlier also. Suppose this is the width of the slit, okay, and we have two slits, but two slits are separated. Therefore, I say here that, okay, this width, whatever I am taking is E, slit width. Okay, this is also the slit width E. This and this are the slit widths E. Okay. But they are separated by a distance D. So therefore, from center to center, what is the value? Can you tell me? From center, from this center point to this center point I am taking, what is the distance? How much it will be? Yeah, roll number 15. Yeah, roll number 15. Can you tell me? 26?
So D plus E.
D plus E, correct. So here you remember this is D plus E plus D, okay? But in case of single slit is only E. And now the light comes and falls on the double slits like this. Now to get it on the screen, this is the screen I am taking. Okay, this is the screen I am using it. On the screen, okay, we will have to see what is the diffraction pattern. For that, again, I have to use a lens to focus this. So this is another lens I am taking. This is the lens I am taking. The light rays which are coming straight away without any modification, that means with zero, okay, diffraction, with zero bending, they will come, and because the lens will make them to focus at one point and we'll get a point here. If I shake it, they will go here. This is undeviated zero earth order. But however, we know that because of small nature of the openings, the slits get diffracted, and therefore the diffracted beam goes by an angle theta when compared to the straight lines. This is theta, okay, and this is also theta. Therefore, these lines now will fall on the lens, okay, and of course I'll take the lens here. Otherwise, I'll do differently with a small inclination so that they exactly fall on that. So they will fall on this, and they will fall by an angle this, and it will fall on this. This is the double slit, okay, by an angle theta. This is diffraction angle. This is diffraction, diffracted beam. And therefore, this will be focused to here by this one, and this goes here and goes here focusing, and this will go and focus here. And a P will be bright or dark, we have to see it. This is the diffracted one. But we know that each slit, we have already seen, single slit gives an amplitude, single slit amplitude. If I want to draw here, we have already derived that single slit gives you an intensity or a theta. We have derived it as some am sine alpha by alpha. Okay, now if you go here, if I just close this slit 1, I call this a slit S1 and S2. If I close S2, it is only S1 operating. Therefore, it should be same as that of single slit. Or if I close S1, if S2 is open, it should be same as that of single slit. Therefore, the diffraction pattern on the screen due to double slit should be containing single slit diffraction pattern as shown here. This is the single slit diffraction pattern. Something it will be there. But if I open both of them, both the slits, if they open, they act as a Young's double slit. In Young's double slit, what we have observed? Anyone, can I have a yeah? In Young's double slit experiment. In Young's double slit experiment, we got interference. Yes, because each slit acts as a two coherent sources. Followed? Hence, in double slit, we have single slit intensity distribution due to this, and we do also have, okay, interference pattern, interference due to two slits, two slits. Therefore, the resultant, okay, the resultant intensity due to diffraction, due to double slit diffraction should contain single slit pattern plus interference. Okay, contains diffraction due to single slit, and it's a product of this actually. Diffraction due to single slit and Also it should contain, okay, interference due to two slits. So therefore resultant is a combination, intensity is a combination or a combination of these two combination. Hence here if I want to draw the figure for these two, suppose say now I will draw the diagram for this. Suppose say I take on this is I'm taking for single slit diffraction and I take here alpha. Then I now write here, okay, the intensity here. You know that, okay, always if I take this is the intensity I am taking. And for single slit at pi, okay, and 2 pi, 3 pi, we have minimas. Minus pi, okay, minus 2 pi, and minus 3 pi, we have minimas. Therefore, for a single slit one, I will get the curve as 0, it becomes maximum, then it falls down at pi, and it again have a maximum, second maximum here, and then falling like this. And if you go other side, here also we have a maximum, central maximum, falls and falls, but falls and falls like this. Okay, this is the single slit pattern, single slit pattern. But we know that double slit should have, okay, interference also. Therefore, it will have the interference pattern also in it. That means I draw here the interference pattern by taking, okay, beta on this. What is beta? We should know here. So I now from here, I say it is point A, I say point B, I drop a perpendicular to this, and this will be the theta, and I'll say C. Therefore, I write here path difference is BC. From the triangle ABC, I write path difference is equal to BC. So therefore, I write sine theta is equal to BC by AB, which I write BC by E plus D, because AB is now E plus D. From here to here, from center to center, I am taking E plus D. Hence, I'll write E plus D into sine theta is equal to BC, which is a path difference. Now I'll write phase difference. Phase difference phi is equal to 2 pi by lambda into BC, and therefore phi is equal to 2 pi by lambda E plus D sine theta is the path difference. In case of single slit, it is only D is equal to 0 because we have only one slit. That is pi. And I will write here, okay, beta is equal to 5 by 2, which is equal to 2. In 2 will not be there here. I am taking this 2 here. Then I'll get is equal to pi E plus D sine theta by lambda. This is beta. Okay, so this beta I am taking on this. If I want to draw the diagram for this, I am taking here the intensity again I. But you know that interference pattern will have alternate dark and bright fringes of equal intensity. That is most important. Therefore, if I want to draw here of equal intensity, that means each of them should be of equal intensity. Okay. Hence, at 0 point, I have, okay, and also I have taken 0. I will take here pi. Again, pi we have maximum. 2 pi we have maximum. 3 pi we have maximum interference. So minus pi, and we have minus 2 pi, and we have minus 3 pi, and so on. Therefore, if I would like to draw the curve for this, we have maximum at 0, goes maximum, comes here, again maximum at pi, and becomes minimum, and again to pi, and minimum, and maximum, like this I will get. But equal intensities. All maximums are equal intensity, all minimum are equal intensities. Okay. So we will get like this. So therefore, these two patterns, this is interference pattern. This is interference pattern. So therefore, a double slit will have both single slit and interference, but the resultant is superposition of these two. Hence, the resultant intensity due to a double slit, I write here and show you something like this. Okay. So the resultant will be, this is now, I take here phi, the phase difference, and I take on this intensity. Okay. In case of double slit, the intensity you can write directly, okay, something like this. Okay. The intensity in this case will be, okay, double slit intensity. From beta, I write the resultant intensity, resultant intensity, okay, I is will be 4 am square sine alpha by alpha square. Okay, this is because of single slit, but you do have this, okay, due to the interference also. So 2 mu t cos r is equal to n lambda. Therefore, I should have a cos term because of interference. So we have cos squared beta. This is the expression for resultant intensity of a double slit. Hence, on this, I will take I. I means, okay, 4a square sine alpha by alpha whole square beta square, cos beta square. Therefore, how it changes, we have to say. To see that changes, I have to write now first the interference pattern. I am writing the interference pattern with the maximum like this at the center, as we have drawn here. And then it falls, okay? Then it falls to minimum. Okay, sorry, it's coming almost same. Therefore, I'll write here, it goes to maximum, falls to minimum, then minimum rises, then falls as secondary maximum. The other side also have to take it. This is the secondary maxima, which fall with that. But what happened to this? We have to say it. Okay. Therefore, the interference pattern will be within this envelope. Within this envelope means this pattern goes, interference pattern tries to go up and up. Okay. So I will take this now to get this one, the superposition I have to see. So to see the superposition, the interference pattern goes maximum up and comes down, and it tries to raise us up. But the diffraction pattern suppresses it. It comes again. It suppresses it. It goes. And it also tries to rise and fall, try to rise. Again coming to here, it raises and suppresses and gives a maximum and gives a maximum and suppresses. So therefore, within the envelope of the interference pattern, the diffraction pattern, we have the pattern for interference. Okay, we have interference patterns like this. So this is interference pattern and this is diffraction pattern. Okay, due to single slit, and together will be the, okay, this is because of double slit. So that means within the central maxima, we have alternate maxima minima of diffraction. And within the secondary maxima, we have alternate dark and bright fringes due to interference. Therefore, we have central fringe system. In the central fringe system, we can see interferences. That means if we have a broad band, in between we have alternate broad in it. Okay, so those are called actually, okay, the interference pattern due to single slit. Here the beta is this, and this beta we'll use again and again for deriving an expression for the N slit. So we have seen now here, okay, single slit and double slit. Now we will look at the N slit. We have seen what happens if there is only one slit. If only one slit is there, we have only diffraction pattern like this. If two slits are there, diffraction pattern plus interference pattern will be there. And they superpose and gives you resultant change like this. Now, instead of one slit or two slits, I have N slits. Okay, these N slits itself is called as diffraction grating. Diffraction grating. Now what happens? We have to see the conditions for maxima, minima and secondary maxima for N slits. Remember that it's very easy because N slits will have N single slits. So therefore, I have a similar pattern of the diffraction pattern due to single slit. But all N slits together will give you the interference due to multiple sources. And therefore, again, N slits diffraction pattern should contain the superposition of the single slit and the interference pattern due to mini slits. So therefore, N slits will have a diffraction intensity pattern consisting of a single slit diffraction pattern over which the superposition of N interference N lights coming from N slits will interfere. They will give you this value. So in the tomorrow class, we will now derive the expression for N slits, okay, diffraction. So all of you here, okay, yeah, I hope you have followed the derivation. These are very important derivations. And for you, the first internal examination is, okay, is including interference and diffraction. So tomorrow class, we will do N slits and we'll see some problems also. Thereby, the syllabus for first internal examination is including of unit 1 entirely, that is waves and oscillations, and also interference and diffraction of second unit. You will have 30 questions, maybe number changes, maybe around 16 to 18 questions you will get, and those questions you have to answer in 45 minutes on modals. So when you are joining into the examination, you join 5 minutes before on modals, okay, and you do it. And then